All right. Thank you very much, Angelo. And thank you very much, everyone, for being here tonight. I am honored to have the position as the last talk of 2024. Thank you for delaying your holidays to be here with us tonight. So this talk is about building a better Postgres read replica. And specifically, what I mean by that is a replica that's faster than the primary. And not like a little bit faster, but a lot faster than running your queries on your main Postgres database. But without giving up anything in freshness, with no stale reads, which means that the queries you run in the read replica are going to give you data that is at least as fresh as the data you would have gotten if you'd run those queries on the main Postgres. That is exactly the response that I was hoping for. There was a remark from the front row that that's not possible. I am making some claims here that I will then caveat, but I hope you will come away from this talk feeling like the fundamental thrust of these claims is, in fact, achievable. Before I get started, I'd love to know, first of all, how many of you are familiar with the company that I work at, Materialize? All right, that's almost everyone in the room. That's awesome. And how many folks here feel like they're comfortable with read replication in Postgres, just as a concept, not necessarily something you set up? Awesome. Great. That will help me pace this. So first up, I want to talk through a web store called Freshmart. It's a pretty standard web store. You go to freshmart.com. They sell cans of soup for $3.99. You add them to your cart. When you're happy with what's in your cart, you check out. Anyone want to guess what happens when you click Add to Cart? It should just add it to the Parker.
Shows up in your cart?
Shows up in your cart. Great guess. Well, it takes a couple seconds. But you know, after a couple seconds, it's not there. Maybe you should just try again, I guess. Oh, shoot, we just spent $211 on soup because we pummeled add to cart 53 times. This is admittedly a little overstated, but I am sure that many of us have interacted with web applications, iPhone applications, where things just don't quite update right. You take an action, that action doesn't seem to occur, and then you realize it actually occurred 53 times while you were pummeling the button. So to summarize the problems here, Freshmart is slow, and it has stale reads. It takes a while for things to add to the cart, and sometimes your cart shows you the state of the world from a couple minutes ago, not the state of the world after you know you just added something to it. And this is really frustrating because the physical world doesn't work like this. When you go to a grocery store in New York and you put a loaf of bread in your cart, you don't look at your cart and realize there's no bread there. And you don't just think, oh, right, of course, I need to wait a couple seconds for the bread to show up. That whole concept doesn't even make any sense. So this idea that actions take effect immediately is something we're very used to in the physical world. But often in the digital world, we throw that concept away, but we do so at our peril because it means that the applications we're using in the digital world don't match our expectations of how the physical world works. But the people who designed Freshmart, they're good developers. They wouldn't have intentionally coded Freshmart poorly. So what went wrong? Well, let's rewind the clock a couple years and talk about Freshmart v1. We've got little Bobby Tables here. He's going to be the star of our show. He loves soup. Bobby loves soup. He's going to be buying soup all night. And the Freshmart developers very smartly used Postgres, a great database, a great backend, a great place to start. And the application is very simple. When Bobby puts the soup in his cart, behind the scenes that runs insert into cart. Bobby gets a response saying successfully added to cart. And then when Bobby goes to look at his cart later, Postgres, super fast right now. It's early days. The logic is simple. It only takes 50 milliseconds. So Bobby gets a nice, snappy response, and he sees that the can of soup that he added to his cart is right where he expects it. Everything's good. Fast forward a couple years, we're on V19 of Freshmart. All sorts of folks now want various discounts to take effect. When Freshmart's running low on stock, they jack up the prices. There's just a lot of complicated things happening. This is the natural course of software. So there's a very complicated query here now that shows you the price of items in your cart, but it depends on 50 other things and a bunch of tables that have to be joined in. And the product managers are running a bunch of A/B tests, and just there's a lot going on. So when Bobby buys soup, that's still fast. All that is insert into cart. But then when Bobby goes to look at his cart, that query takes 10 seconds. It's just really slow. But Bobby's a loyal FreshMart customer. He keeps using FreshMart. He's pretty happy that he's adding soup, and he's seeing his soup, and everything's at least obeying the rules of the physical world with respect to consistency. Oh, but then FreshMart goes viral. Maybe there's a COVID outbreak at Bobby's school, and all of his friends have sore throats, and they all need to buy soup, and they all need to buy soup right now. So our poor Postgres application server, or database server behind the application, it caught on fire. It was doing really well, but it's just too much load for this Postgres to handle. Remember, looking at the cart is a lot of work. It's a 10-second query, so that pretty quickly jams Postgres up. So what do you do in a situation like this? The time-honored technique is that your SRE team goes out, stands up a Postgres read replica. This works great because you can take that really expensive read query, it's just a read query, and move it onto a separate machine. And you could even have 10, 15 Postgres read replicas. Not depicted here, can't fit them all on the slide, but imagine that maybe there's more than just one read replica. And the magic is that there's one primary Postgres. It still has to handle all the writes. That's just how Postgres works. Someone needs to decide if multiple people are using FreshMart at the same time. Only one of them can get that last can of soup if they're about to run out. And the primary Postgres needs to be that single point where those decisions are made. But once those decisions are made, the primary Postgres can stream those decisions, the writes that have occurred, to the read replicas. And then the read replicas now have a full copy of the database. This process is happening continuously in the background. And so you can direct your read queries to the read replicas, and that load no longer goes to the primary. But let's take a look at the problem that this causes. Bobby puts his can of soup in the cart, and then he goes to look at his cart. But he gets now routed to a read replica. And there's a race going on. Bobby is talking to the read replica at the same time, but the primary database is talking to the read replica. And it's pretty easy to lose that race. And this is what caused that inconsistency we saw in FreshMart earlier. The knowledge of that can of tomato soup being in Bobby's cart hasn't made it to the read replica at the time the read replica starts processing Bobby's query. And then it still takes 10 seconds. And actually, the can of soup arrives at the read replica partway through processing the query, but it's too late. Processing the query has already started. And in the end, Bobby gets a result that, from his perspective, is wrong. There's no can of soup in his cart. So let's formalize this a little bit. What's exactly going on here that feels like our head is exploding? In the database literature, this is called a violation of external consistency. You might also hear the term linearizable. I try not to use the term linearizable because it has a number of different definitions. One of them is external consistency, but it just muddies things up. So I'm going to try to use the term external consistency in this talk. But if you hear someone else talking about linearizability, it's probably the same thing. External consistency also has a slightly more intuitive definition. It's not amazing terminology, but it's better. The idea is, imagine that you're a user. You're an external observer of the database system. You're not the database itself. You're external to the database. All external consistency requires is that once you see an operation commit, O1, all future operations, O2 and beyond, will observe the effect of O1. It's basically just saying that your database works like the real world. If you take an action, you observe the effects. But there's an important thing to call out here. External consistency does not say anything about transactions that overlap. It only applies in the case that you observe the commit and then you start something else. If little Bobby tables and his older brother, big Bobby tables, are both using FreshMart at the same time and they race and one of them adds something to the cart and the other one looks at the cart, it's actually undefined what the guy looking at the cart is going to see. He might see it there, that can of soup that his little brother is adding, or he might not. External consistency doesn't care in this case because these are considered to be concurrent operations. So looking back at that same diagram, this is a clear violation of external consistency. Putting something into the cart, O1, we get a commit, and Bobby sees it, and then Bobby starts the transaction to look at his cart, and he doesn't see the can of soup that he just added. So formally, this is called a violation of external consistency. Is this all making sense so far? Excellent. All right, so with this knowledge in hand, it's now very easy to build a better Postgres read replica. There are two problems. It was slow, and there were stale reads. So let's just be fast and be correct. What could be hard about that? So to be fast, step one, spend 5 years re-implementing Postgres to have an incremental computation engine at its core. That's what we've been doing at Materialize. Unfortunately, I don't have time to go into it, but there's been a lot of ink spilled on how Materialize works, and a lot of talks as well, if you're interested. At a 10,000-foot view, Materialize works by taking your SQL queries as materialized views and then automatically updating them. So you have to pre-declare your queries as materialized views. That's why it's called Materialize. And then Materialize listens to your Postgres. It subscribes to the change feed. Anytime the data changes, Materialize just updates in place the materialized views that you have requested it to maintain. And then when Bobby shows up asking about what's in his cart, that's a fast, cheap operation because Materialize has already done, if not all of the work, like 99.9% of it. And the really key insight about the power of incremental computation is that it lets you do work proportional to the changed data. So even for a data set that's hundreds of gigabytes in size, the amount of data that's changing second by second is usually pretty small. Tens, hundreds, thousands, maybe tens of thousands of updates. But Materialize each second only needs to do work proportional to the amount of data that's changed, which means you can get these crazy speedups because most of the time, 99.9% of the data has already been processed by Materialize. And you just have to do a little touch-up to that data. Now, for the simplest example of how incremental computation works, consider a query select count star from T, just a very basic count in SQL. The state for that query is just a counter. It starts at 0. When you add soup, it goes up by 1. Now the count is 1. You add crouton, count goes up by 1 again. Now the count is 2. If you then remove soup, the count goes down, and now the count is 1. It turns out this basic technique generalizes to far more complicated operators, filters, other aggregations like min and max, window functions, joins, and joins are really quite complicated, and that's where a lot of the innovation in Materialize has occurred. Pardon my automatic Okta login. But this is the basic idea. You maintain some state, and that allows you to very efficiently process records as they come in. You don't have to recount everything when you get a new record. You just increment or decrement the counter that you've been keeping track of. So that's the basic idea. Check. We're faster than Postgres. And I'll circle back on this. The thing I want to focus on, the thing that I think is really interesting, because it's a relatively small insight with a really big impact, is how to eliminate stale reads. And I'm calling that correctness here. The query is correct if it does not have stale reads. So eliminating stale reads is the same thing as saying preserving external consistency. We want to get rid of all of those external consistency violations that FreshMart was having with the introduction of that read replica. So let's reimagine the definition of external consistency from the perspective of a read replica. What it means, if you're a read replica of Postgres, to preserve external consistency, is that anytime a query shows up, you need to make sure that you have all of the rights that have been committed to your upstream Postgres server. And the answer that you give must reflect all of those upstream rights. So let's say it usually takes about 100 milliseconds for a transaction to make its way from the primary Postgres server to you, the read replica. You could just wait 100 milliseconds. That would probably be fine, right? But networks are asynchronous and unreliable, and maybe there's a delay. So maybe you should wait a second to be safe. But what if there's a network partition and it's actually going to take minutes, or maybe that server's never coming back? All sorts of things could go wrong. And if we want to be perfectly correct and never have an external consistency violation, not just a small probability, but truly drive it to 0, we need to do something more than just waiting for what feels like the right amount of time. I need to take a brief detour and talk about how Postgres represents changes. So the way that that primary Postgres server communicates with a replica, whether that replica is a real Postgres replica or Materialize, is via what's called the wall, the write-ahead log. And the wall is actually so simple under the hood. I think it has a relatively scary name, and it looks kind of scary. But all it is a list of every transaction that's been executed against your Postgres server with its contents. It's basically just the SQL that's been written. We can see here there was a transaction that began, 2 orders got inserted, and then that transaction committed, and then there was another transaction that deleted one of those orders, and on and on and on and on. And of course, Postgres doesn't keep the wall around forever because it can't. But logically, the wall began when you started Postgres for the first time, and it just wrote down every transaction that you sent it that committed in the order that it committed. And what the wall gives us is this really powerful ability to reason about how far behind our read replica is. So the primary, by definition, by virtue of being the primary, is always at the end of the wall. The primary knows about everything because if the primary doesn't know about something, it didn't happen. But the read replica is almost always going to be a little bit behind the primary, if it's healthy. If it's unhealthy, it might be way far behind, but ideally in the steady state, it's lagging the primary by just the latest few transactions. But we have these log sequence numbers, LSNs, reflecting the various transactions that have occurred, and we can say, this read replica is only seen up through this transaction. Or actually, let's just wait for the read replica to catch up until it's seen this transaction. So this kind of log sequence number calculations, this kind of reasoning, allows us to build a consistent read replica that doesn't experience stale reads. So what's happened here is we've swapped out the original Postgres read replica that FreshMart was using for Materialize. And this picture is mostly the same. Postgres is streaming data to Materialize. Here I've represented the various LSNs representing the transactions that have committed. So at some point in the past, we got up to transaction 4. Postgres sent that data to Materialize. Then Bobby adds his can of soup to the cart. This is LSN 5. Bobby doesn't actually know this, but under the hood, Postgres wrote it down on the wall at position 5. And then Postgres is like, all right, I got to tell Materialize about this, and starts very slowly telling Materialize about LSN 5. At the same time, Bobby is curious what's in his cart. Did that action work? And this gets routed to Materialize, because Materialize is serving all read traffic for FreshMart now. And all Materialize has to do to serve a perfectly consistent read is just ask Postgres about what data it has that Materialize doesn't have yet, if any. So Materialize runs a very fast and cheap query against Postgres. Select PG current wall LSN. It does exactly what it says on the tin. It tells Materialize what LSN Postgres is currently at. And Postgres goes, oh, hey, Materialize, you're at LSN 5. Or I'm at LSN 5. And Materialize just needs to wait then, not for 100 milliseconds, not for a second, not for a minute. It just needs to wait until LSN 5 shows up, whenever that might be. And that gives you this perfect consistency. You're not waiting for some arbitrary point in the future. You know exactly what LSN you need to see to be up to date with all of the commits that Bobby could have possibly observed. You might see a couple more transactions that happened in here, but you'll not see less. And that's the key property that we have to uphold in order to provide external consistency and eliminate stale reads. And this is a really key point. You really need to wait until Bobby submits his query before you ask Postgres what the current wall LSN is. This needs to be a causal chain. You cannot send this query off until Bobby has gotten his query to Materialize. But if you follow that strict ordering, you provide external consistency, and the data returned by Materialize is going to be as fresh as if Bobby had ran that query against Postgres directly. Now, there's a bit of a problem here. Postgres is on fire because it was serving too much traffic. And we got to pull a lot of that work off to Materialize. But now every time you talk to Materialize, Materialize is going to talk to Postgres, which kind of reintroduces the problem. It's better because this is a really cheap query, and we used to be running a really expensive query. But it's still really chatty. That's not ideal to have this bottleneck in your system. It doesn't scale as well as you might like. The good news is this protocol admits batching really well. It's not that you need to ask Postgres about every query that arrives at Materialize. It's just that you need to ask Postgres at least once after the start of the query. So if you get a query in Materialize, you can wait maybe 10 milliseconds, maybe 50 milliseconds, maybe 100 milliseconds, maybe a second. You can dial this around. And you can gather up more queries and then ask Postgres for the current wall LSN. And whatever Postgres says here is valid to prevent external consistency violations for any of these queries. And then you just repeat that process over and over again. So this is a pretty cool optimization that prevents your single point of bottleneck, your primary Postgres server, from falling over under the load of these queries that eliminate stale reads. One of my favorite parts about this protocol in Materialize is that it's not limited to just Postgres, and it's not limited to just one Postgres at a time. I brought MySQL into the mix here, but you could bring any number of MySQL instances, any number of Postgres instances, and really mix and match. And the protocol just generalizes really neatly. Whenever a query arrives at Materialize, you look at it and you say, is this derived from data in Postgres or MySQL or both? Okay, let me go talk to all of the upstream systems that provided data that my query is derived from, figure out their current, for Postgres it's LSNs, for MySQL it's GTIDs, transaction IDs, figure out their latest transaction ID or LSN, and then just wait. Wait for this really slow message from MySQL to arrive, wait for this slightly less slow message for Postgres to arrive, and you've got to wait it all out before you return that data to the client. And the term we have for this internally at Materialize is real-time recent. We say this data that's returned is guaranteed to be real-time recent. We're still workshopping this phrase. This one came to us from Kyle Kingsbury, so it certainly carries some distributed systems weight. But it's not immediately obvious to our users what it means when we describe data as real-time recent. But the point is, this does not have any external consistency violations in it, which is a really nice property when you're building applications. So that's it. We did it. 5 years of work. Now we have a faster version of Postgres. And we've eliminated stale reads with this relatively simple protocol to just chat with the Postgres primary before we respond to a query to make sure we have the freshest data. One thing that's really nice about this protocol versus other attempts to provide this guarantee like synchronous replication is sometimes used, is that there's no availability impact to the primary. If Materialize goes down, the primary can keep serving traffic. With synchronous replication, the protocol is the primary must chat with the read replica and force that read replica to come up to date before it tells the client that the can of soup got added to the cart. But that means if the read replica ever goes down, the whole thing goes down. You can't work with the primary anymore. So SREs tend not to like this. And what's really nice about this protocol is the impact is limited to Materialize. It's a relatively cheap query. We're careful to batch it up and only run it infrequently. And if Materialize goes down, only Materialize goes down. The primary can continue accepting writes. All right. I may regret this, but I'm going to try to do it. I'm going to try to do a live demo here to prove to you I'm not making this all up, but also to give you a sense of what the limitations are here. All right. So over here on the right, is this large enough for folks to see? I don't know that I can make it too much bigger, but I can try to be a little more verbose in my explanations. Get this set up. All right, so this is a Postgres primary, and this is Materialize. And we have this very complicated query that's computing the price of items in a cart, let's say. Don't worry about what's in here. This benchmark is published if anyone is curious, but the point is it's just a very complicated query. And what we can do is ask Postgres what the current price of product ID 1 is. Let's assume product ID 1 is that can of soup that Bobby has been so diligent in purchasing. And what you'll see is this is really quite slow. This query takes, I want to say 13 seconds to execute. Yep, that came back in 12 seconds. So this is a very expensive can of soup. It's $772. And it took Postgres 12 seconds to figure that out. Let's use Materialize just to subscribe to changes in price of this can of soup. So subscribe is one of the killer features of Materialize. It lets you see the results live update. And let's go ahead and turn on some promotions for this can of soup. This query is specifically written in a way that I can run it over and over. I'm just turning some promotions on if they're off or off if they're on. And you see the price just jumped to 804. If I turn the promotions off, we should see that pop down to 772. And this continues forever. Now I want to race Materialize against Postgres. So what I'm going to do, if I am fast enough, is I'm going to really quickly press enter over here, and then I'm going to jump back to Materialize and press enter. And that's going to simulate the price is getting updated, somebody's doing something on the app, they're causing a write, and then they're reading from Materialize. And what this query is I'm toggling some promotions, and then I'm immediately reading from Postgres. So Postgres, by default, this is all on the primary, provides external consistency. So I'm guaranteed that this query that tells me the latest price will reflect the change in promotions that I just effected. Then I'm going to run over to Materialize. I'm going to hit Run Query. And hopefully, because we've got this complicated machinery in Materialize to always provide external consistency to eliminate stale reads, hopefully Materialize won't give me a stale read. All right. Pressing Enter, and then running the query in Materialize. Oh, 1 second. It's an optional feature. So let me just run that again. Again, I'm going to hit Enter really fast and then jump over to Materialize. I canceled the query. The third time, though, it's going to be the charm. Give Postgres a second. All right. This time for real. Press Enter. Run query and Materialize. There we go. All right. Materialize was able to get us the answer in 576 milliseconds. Postgres, still chugging along. Still hasn't told us what the answer is. Another couple seconds, it should, and it should agree. And yes, we see the same 772 price in both places. Thank you. And let me go for broke here. I'm going to try to do this one more time so you can all see that it wasn't a fluke. Enter. Run. 401 milliseconds this time, and we should see those promotions are no longer in effect, and Postgres will also tell us that the price is 804. And yes, an ill-timed Okta pop-up, but the proof is still there, 400 milliseconds for Materialize and 11 seconds for Postgres. So that's it, that's the demo. Let's talk about some limitations now that you've seen it in action. OK, so a few limitations that are fundamental to Materialize. First of all, Materialize isn't always cheap. For particularly complicated queries, Materialize has to keep all of that state in memory. And it has to keep it in memory in perpetuity for as long as you want results to be fast. So that can be expensive. You have to go buy RAM. You pay us for that RAM, and then we ask Amazon for it. But you're still footing the bill for it. You also need to know your queries up front. This is, for a lot of applications, no big deal. But for some applications that are really dynamic, that are mashing SQL string, Materialize is just not going to be a good fit because you can't pre-declare the stuff you care about as Materialize views. But for FreshMart, there was an obvious thing to turn into a Materialize view, which is what's in the cart and what's the price of everything in the cart. Then there's some self-inflicted slowness here. Ideally, we'd like response times to be as good as FreshMart was in the early days of 50 milliseconds. And what we were seeing was 400 milliseconds, 800 milliseconds. That's largely self-inflicted right now. Materialize sources tick every second. So for reasons of efficiency, we only bring in updates from Postgres every second. We can dial that down to 500 milliseconds or 300 milliseconds without too much trouble. But diminishing returns, it's going to be hard to really get that down to 100 or 50 milliseconds. Fundamentally possible. No reason that we can't get there eventually, but we're not there yet. And part of what makes this slow is that we write to S3 on the critical path. So any data coming from Postgres goes to S3, and then it goes to the Materialize view. So you have a write to object store on the critical path, and that's why it's going to be hard to get it below like 200 milliseconds, at least for the P99. But those are limitations that are fixable. These are the two limitations that you'd really need to go with a different architecture to get around. What's cool is that half of this work doesn't need to be locked up in Materialize. Yeah, the minimizing execution time bit, you need an incremental view engine. There is some work to bring that to Postgres, if any of you have seen PGIVM. I think it's largely the work of one guy, and it is not nearly as feature complete as Materialize. It's not ready for prime time. But maybe one day, Postgres will get support for IVM in core. But eliminating stale reads, this protocol is not all that complicated. And in my limited searching of the Postgres mailing lists, I was actually able to turn up some exciting work that's ongoing right now. The first is the addition of a PG wall replay wait function to Postgres. So this isn't quite as smooth as Materialize, where Materialize handles that query for you. But if you did your own LSN tracking, maybe in your application, whenever you were querying the read replica, you could pass in the LSN from your last write and tell that read replica not to respond to any queries until it was up to date with that LSN. And then you know that any queries you do from that point forward will reflect the results of that write. So you can stitch together your own external consistency that way. There's also some really cool work ongoing with transparent handling in PGWire. So if you're using PG Bouncer to automatically mediate requests between the primary and the read replicas, the protocol could learn to pass LSNs around in just the right way, and then you don't need to think about it. And that would provide an experience similar to Materialize. All right, that's it. That's the talk. Thank you all very much. I do want to make a quick shout out to all the other people who contributed to this work. I actually did very little for this. I'm just excited about it. But my co-founder Frank had the original idea and worked with Kyle Kingsbury on it. And my colleague Sean Loisel wrote the initial implementation. And another colleague of mine, Petros, is the one who maintains all of this code today. All right. Any questions that I can answer?
And repeat them.
And I will repeat them. Yes?
Is there any reason why you can't return the LSN with the write in response to the write, so that you don't have to send a second query to get it back, and then maybe there's some things in between that take a while to come through?
Yeah, so I think this looks a lot like what Postgres is potentially adding as part of this transparent LSN protocol. But with this work, the LSN would come back as part of the network protocol, so then the client would have it.
So it's just that you didn't have a place to put it in the...
Exactly. It's just, there's literally nowhere to put it in the Postgres network protocol right now. But with this, Bobby would have it, and then Bobby could send it along with any future queries that he issues. And now, in this case, it's the Postgres read replica. But if this were Materialize here, Materialize could go, oh, you want us to wait for LSN 5? No problem. Great. We don't even need to chat with Postgres. You gave us a very specific LSN to wait for. We'll just accept that. We'll take your word for it. So yeah, I think that might be coming. I am not familiar enough with the Postgres community or the way Postgres does development to know whether this patch is a slam dunk, it's going to fly through, or whether it's going to be debated for the next 5 years. I have my suspicions, but yeah, I put the links in the presentation, so if anyone's curious to subscribe, you can find them there. Yeah?
Two-parter.
Great.
First part is the fast one. Does the client right now, when you're using Materialize, need to keep track of it, or does your library handle that?
So the first question was, when you're using Materialize, does the client need to keep track of it? And the answer is, let me see if I can get back to it. The answer is no, the client doesn't need to keep track of anything, because it's actually all handled inside of Materialize. So when we do this query, we get the latest LSN, and then we wait for it. But the client, I put the LSN here. I kind of wish I didn't. The client actually never sees LSN 5.
Yeah, that was the part that I was...
Yeah, sorry. Just the diagram wasn't particularly well labeled there.
No worries. The second part was for the actual Materialized view, you said you keep it in memory. How do you handle the scaling of it if you're going to OM for some reason?
Yeah, so the question was, how do we handle the scaling of Materialized views? Does it cause ooms? And the answer is, yeah, this happens all the time. It's one of the biggest pain points of using Materialize. We make it easy to scale up the cluster that's hosting your Materialized view. So everything's done in SQL in Materialize. So you type create cluster, and then you type create Materialized view in cluster. And then you can alter cluster set size 2x large, 4x large, 8x large. So you can scale it up. We have plans to build auto scaling. And it does actually spill to disk in some limited cases, but disk is not performant enough for a lot of queries. So it's like running any software. You have to keep an eye on the memory usage and make sure that you have enough headroom in all your clusters.
Do you replicate the Materialized view because you're writing to S3 and then you can fan out the read?
Yes, the question was, do we replicate the Materialized view? Absolutely we do. You can see here the results are going to our storage layer, which is just S3, before they go back to the client. So you can have any number of serving clusters all reading off that same Materialized view. So we give you a lot of flexibility to slice and dice, which is great, but it's also it's Legos that you have to stack together sometimes, and that can be an operational challenge. Yeah, Pete.
How much mileage do you think FreshMart would get out of horizontally scaling their data or sharding their database? Maybe using our former employer cockroach versus this approach, and can you do both somehow?
Yeah, so Pete's question was, shouldn't they just use Cockroach, a product that both Pete and I worked on in a past life instead of Materialize? And it's a great question. And the thing that you wouldn't get with Cockroach is a solve for the problem that the query is just slow. Like if this query takes 10 seconds to run on an OLTP system, it doesn't really matter if it's Postgres or if it's Cockroach. Without incremental view maintenance technology, like adding a read replica doesn't help. The read replica just runs it in 10 seconds as well. So that's really the key reason that FreshMart wants to switch to Materialize, and it's also what we see with our prospects and customers. They're interested in Materialize when they have queries that are just too slow, and then what we're hoping to offer them is an experience without the trade-off of stale reads. Do we have time for more?
Yeah.
Back left. My left, yes.
Can the Materialize view itself be sharded? So like large view, just multiple workers?
Yeah, I should have mentioned, large cluster sizes in Materialize will automatically shard the computation across multiple machines. So it's invisible to the user. You have small, medium, large, extra large, and at some point we'll recruit multiple EC2 instances, but you don't have to worry about that. That just happens automatically. Back right.
Yeah, thanks. On this slide, if I understand correctly, the problem is like replication delay. With the proposed solution, doesn't this put the replication delay into the query time, like having to wait from that LSN into the replication? And how does that impact the production system?
Yeah, so the question was, doesn't this put the replication lag into the query? Yeah, it absolutely does. And that's kind of the trick here. That's why it sounds impossible, and when you dig into it, it's like, oh, okay, it is possible. But the cost is your queries are slower. But this is a pretty fundamental trade-off in database systems. You can get you can get stale reads fast or fresh reads slowly. So this is still not quite ready for prime time and Materialize. Like those 500 millisecond response times are not great if you're trying to write a production application. If we got them down to 100, 200 milliseconds, I think we're in business. So it's still early days to know exactly what the number is that makes people go, oh my God, freshness is worth it, give it to me, I want it, versus, a little bit of staleness is okay, Bobby's not refreshing the page that quickly. So I think that's a pretty fundamental trade-off though, and it's just about can you do enough performance work to get the numbers where you need them to be. Yeah, Phil.
You have said a couple times that you have to only wait until at least the LSN caught up, and I'm confused why that is going to give you consistency. If it went past that, how are you still consistent? Like, because within your transaction, you want to be only at the LSN that was committed for that transaction, right?
Yeah, so that's another trick with only caring about external consistency. So the only bound that external consistency imposes is that once you see an operation commit, all future operations include the results of that, but it doesn't say only those results. It allows additional results to have happened. Like if Big Bobby Table showed up here and did something, then it would be totally fine for O2 to include the results of that as well. The other piece of consistency that people often talk about is serializable versus repeatable read versus read committed. We don't have to worry about any of that with Materialize because we're just a read replica. I think the thing that you're asking for is like, I'm going to do a write, and then in the same transaction, I want to do a read. And we don't have any special tricks here for that. This only works if you're willing to split your write and read across different transactions, and you want external consistency across them. But if you want that read to happen at the specific moment after your write, you have no choice but to put it in the same transaction that the write occurred. And in that case, yeah, Materialize doesn't help you. You just got to do that all in the primary. Did I understand that right?
Maybe, but now you kind of be more confused because if you split the write and read across different transactions, how are you expecting any consistency? Like, what does consistency even mean then?
Right. So the example that works for my brain is the one with the FreshMart situation where there were two transactions that occurred. There was the add to cart transaction, and then there was the look at my cart transaction. And the external consistency guarantee that I want is that if nobody else did anything, it's my cart. I know my brother, Big Bobby Tables, is not using FreshMart right now. The only thing I want is if I know that I executed a transaction to put something in the cart, and then I go look at the cart, that the thing I put in the cart will be there. But these are separate transactions from the database system's perspective. Does that help?
I'll let other people ask.
Sounds good. Yes?
We've implemented something similar at Offset. We
Awesome.
also called it Materialize. So I saw you have something called subscribe.
Yes.
Pushes you changes.
Yes.
What we've seen is you were returning a scalar, which is pretty simple. What if that returns like 10,000 rows? We're seeing problems where sending that many events to the client just kind of blows up, especially if a lot of things are changing that query at the same time. How do you guys handle that?
Yeah, so the question was, what do you do when subscribe produces so much data that the client falls over? We don't do anything special. We just make it the client's problem. If 10,000 things are changing every tick, we'll send them all to you, and if you can't handle that, we don't really have anything else we can do. Maybe there would be some way to optimize the diffs if it's just sending all that data over the network. That's the problem. We don't do anything like that right now, but at the end of the day, if you can't handle the fire hose as a client, there's not a whole lot to be done other than optimizing the client, at least in my experience.
Do you fall behind processing those updates?
Materialize does not, but the subscribe will build up, and you might actually run Materialize out of memory. The question was, does Materialize fall behind? So there's resource requirements on Materialize to keep all the unprocessed changes around. So if you can't keep up with them, yeah, that could eventually cause a buffer to overflow in Materialize. But other clusters would be isolated. There's ways of making sure that each client is isolated. Yeah.
I think
We're out of time. All right. I will stick around for a while, folks. So if there are any more burning questions that I can answer, I'll be here for them. Thank you so much.